going to show you guys also. And I do some research work, extremely important. We have to come up with new things all the time, and so I do a lot of R&D stuff, so that I can basically make my seminars better and give more and more information to people. And it's all available for free on my websites and articles and all that stuff. I wrote the book on scientific molding, robust process development, and scientific molding. It's now in the 2nd edition. I'm working on the 3rd edition. It's been great demand from the industry, so thank you all of you who have the book. There's a free app for scientific molding on Google Play as well as the App Store. Please feel free to download that. It does not have DOEs. It has a scientific molding side of it. I do a lot of seminars. This is my location here. I'm sitting here right now in Southern California and San Diego. That's a molding machine that I have, and I do training on that. And there's a classroom at the bottom that you see. Of course, this is all pre-COVID, yeah, but now that has now been transformed to, I have a class coming up next week, and using social distancing, so I've limited the number of people to 6, and I've blocked those things up so everybody sits in their own cubicles, and I practice social distancing. I have these classes every month, by the way. So the schedule is always on the website. And so if you guys are interested, please sign up. I train, do in-house seminars too, all over the world. I've done these things, right? So my personal goal, right, this is very important, right? Is that I've been in business since 2000. My personal goal is to provide easy tools, easy to use tools for molders. That's one big thing that I want to do, right? There's this fantastic research being done. There's fantastic technologies out there, a lot of the stuff, but I want to somehow translate that to the people on the production floor, and that's what I've been trying to do. And of course, to help molders make data-driven decisions, right? So with the software, which I'll show you, which is a DOE software, right? When I first said I want to make my own DOE software, because I was using Minitab, which is a fantastic software, right? For those of you who use Minitab, you know the capabilities of that. It's a fantastic software, but it's not easy for a molder to use. Okay, and so I said I want to come up with something simple that anybody without any math background can use it, and that's how the software is today. So when I started looking for somebody, I found Ravi, right, which I'll introduce here, right? So Ravi is my partner in the software. He's a mechanical engineer by trade, and he has specialized in data analytics and quality systems for the last 30 years. He's actually online. And so when I met Ravi, he, even being a businessman, he said to us, why do you want to develop a software? He did not say, okay, let's do it together. He said, why do you want to develop a software? I said, I want to develop, he says, because there's so many of them out there. I said, I want to develop my own software only because I want to make it easy for people, right? And that's how we became partners in this stuff. And it's been, you'll see, it's been now, I've known Ravi, the software is, by the way, 20 years old, actually more than that, right? And I've known Ravi for the last 12 years. Again, we have had a fantastic relationship on this, right? So what are the typical, so let's get into the presentation, right? That's just introduction there. So what are the typical problems of a molding company? And I'm sure all of you are going to relate to this. Technicians to constantly adjust the molding process. Parts have to get sorted out of the machine. The parts that need to get sorted out by cavity. Don't tell me you guys don't know this, right? Sometimes cavity 4 is the one that's bad, so you have to sort it and throw it away. Measurement frequency is very high. Possible customer returns, right? That affects your reputation. You have to rerun the parts, all that stuff, right? Tool engineer frustrated because they have to add steel to the tool. These are only some of the problems, by the way, right? They had the tool done correctly, but then you said, no, this part is now too big. So they go, change the steel, but now you have to go back and weld it, right? Some typical things, right? Parts were good. CPKs are acceptable during qualification. So you qualified the mold, fantastic, 1.67 CPK. Now you go in production, my God, now the CPK is like 0.97. What happened here, right? So all these things are typical problems in the production floor. Simple question. If you want to drive your car in cruise control mode at 80 miles an hour, right, with no stops for 4 hours, that means just want to keep driving, yeah, right? Which of these roads would you prefer? The answer is very simple, right? Do you want to basically drive on the edge of a cliff, or do you want a nice wide freeway like this, right? So of course, the answer is obvious. You need to have a nice wide freeway so you can have carefree driving. There's your left limit, right limit. You get a phone call, you want to drink water or something, a bottle or whatever it is, and you waver a little bit, you're still going to be okay, right? So the choice is always having a nice wide freeway for cruise control, and I say therefore molding processes should also run under cruise control mode and also should have a nice wide freeway, right? We do not want a process that is at the edge of a cliff, right? And therefore molding processes, they must be robust, they must be repeatable, and they must be reproducible. All the three R's are extremely important. Okay. Now, having said that, if the process is on the cliff, then all those problems that we talked about, you're going to see all those problems. All right. So robustness is one thing I talked about, and I said the process should be robust. So when you say that, that means a process should produce all the parts under normal variations in the production environment. Okay, so if you see what is that, if you look at what does it take to mold a part, right? There's a certain path to that, right? So each of these things is going to have variations coming from, the process is going to have variations coming from different locations, the machine, the personnel, the process, and all these things. And at the same time, each of them are going to have their own fishbone diagrams, right? There's going to be variation in process. There's going to be variation in the measurement systems, right? So that's why you do gauge R&R, right? It's going to be the variation in the viscosity of the material, right? So all these things are going to happen. So they're all going to have their own fishbone diagrams. Now, apart from this variation, please also remember that to come up with a good molding process, there are 5 elements that are important: part design, the material, the mold design and build, the molding machine, and then last is the molding process, right? So all these elements also, this is pre-production or pre-molding. Okay, all these things are also, these 5 elements are also important. It's like a relay race, right? All the runners in the team have to run fast enough to win the race, right? So this is very important to know. So if you look at the aim of a molding operation, what do you want to do? You want to mold parts consistently. You want to mold all the parts that meet all the quality requirements, and you want to run an efficient process. Consistency, 3 types of consistencies. The first one is a cavity to cavity consistency. Second is a shot to shot consistency. That means every shot has the same dimension. And then you've got a run to run consistency. That means you mold 100,000 parts, you change the mold something else, change the mold back to the first mold. If this quality of the parts and this quality part is the same, that means the average and the variation that you had in the first run is the same as the average and the variation that you have in the second run, then we say you've also achieved the run to run consistency. This is the most difficult consistency to achieve for a lot of molders. Okay, why? The main reason is the word I used sometime back: robustness. The process was not robust to begin with. It is not repeatable. It's not reproducible. Okay. Of course, you want to meet all the quality requirements. You want to have a good, efficient operation, and you don't want a process that runs like this, right? So this is where you see a lot of loss in efficiencies. You see a lot of returns and so on and so forth. So something like this is not acceptable. All right. So going back to this, the source of variation can come for a molded process part. It can come from various locations. However, we are going to focus on the process, right? So this is the first one I just showed you, the process, right? So now if you look at the molding process, where is the variation coming from? Number of things, but we are now going to be talking about the process conditions or the molding process parameters, right? How many are there? I have identified them as 11 plus 2 molding parameters on the machine, okay? And 8 outputs. So these 11 plus 2, I don't say 13, because if you don't split the pack and hold into 2, and a lot of companies don't split pack and hold into 2, then you have 11, and thus if you do split them into pack and hold, then you have 13 parameters out there, right? And decompression is there. It's a question mark. Again, I cover this in my 4-day class. I teach a whole 4-day class about it. So let's not look at this, but I say that is 11 plus 2 molding parameters. So variation in this is going to give you variations in the quality of the molded product, right? So here's the injection, the complete molding cycle. Therefore, in order to have a good, robust process and to have a good cruise control process, then you need to optimize your molding process, right? And so what do people do? If you look at the process development procedure right now, you have got the injection, pack and hold, cooling, during which screw recovery takes place. This is a wholly complete plastic conditions that you need to optimize. What do molders do? The first thing they'll do is the melt preparation studies. I don't know if a lot of people do these things now, but again, there's something that I've been teaching for the last now 5-6 years, is that there's a melt preparation study. So you do melt preparation, screw rotation speed study, a back pressure study for coming up with this part of the cycle. And then you get into the scientific molding side, or which I call as a 6-step study. The only reason I call it 6-step study because so we know how many steps there are. It's nothing else. It's not that I wanted to come up with something else. The term scientific molding was coined by Mr. John Boselli and the folks at RJG, right? So, and these are the 6 studies for that, right? So people will do these studies and they come up with the process. So here are some graphs from that. Melt preparation study, the 6-step studies, viscosity, cavity balance, pressure drop, process window, gauge seal study, and then cooling study. So they do these studies and then they come up with the molding process. Most companies, right? So here is the molding process that I've come up with after I have done the scientific molding studies. Okay, good. So I have a process. So are we done? Right? The answer is no, right? Why is that? Because what about long-term variation? Are the dimensions that we measured, where are they? Are they on the cliff? Right? A lot of people will do a CPK study right there, the dimensions get, see, but it is flawed because if you take 30 parts back to back and do a statistical analysis, chances are they'll be extremely consistent. But that is not the representation of your complete production run in the future or the next one that you're going to get, right? So are the dimensions you measured, are they on a cliff? Are you going to be fighting dimensions and cosmetics at the same time? Yeah, I'm going to give you an example of this, right? Are you setting realistic alarm limits, right? Alarm limits, very important. You say that alarm should, the cushion value should be plus minus 0.05 inches. Where do you get that 0.05 from? The pressure values should be plus minus 100 psi. Where do you get 100 psi from, right? So there has to be some data-driven decisions you need to make, data-driven numbers you need to come up with. If there's a dimensional issue, what should I change out of the 11 plus 2 parameters? Right? As an example, look at this, right? The dimensions below the lowest spec limit. So if you want to make a part bigger, increase the dimension of the part, then if I say go increase the dimension of the part, what will you do? Possible solutions are you reduce the mold temperature, you reduce the melt temperature, you increase the pack pressure, you increase the hold time, you increase the cooling time. All these things will, in theory, increase the dimension of the part. Yeah, and therefore we need to understand the effect of the molding parameters on the part quality, which is the one that is going to give you the biggest bang per buck when you go change. Is it melt temperature or is it mold temperature? And there's no definite answer because it is part dependent, it is dimension dependent, and it is material dependent. Okay, all these answers are correct, but they're all dependent upon the particular things I just told you about. Okay, so we need to understand the effect of molding parameters on the part quality, right? And that is what is design of experiments. We play with the process. What do we do? Let me go change the cooling time and see what happens. Let me go change the packing pressure, what happens, right? So we play with the process. Playing with the process and systematically finding the effects of what the effects are is basically what is called as design of experiments, right? So if you look at a definition, it is a systematic set of experiments that involves changes to factors of the process to study and recording the corresponding effect to the responses, right? So that is what a DOE is, right? Now DOEs is nothing to do with injection molding only, by the way, right? It has been around for a very long time, all right? So I got this from online from psu.edu, where you can see how the history of DOEs came about, right? From R.A. Fisher in 1980 to 1940s. He used it in agriculture. And for those of you that studied DOEs, you probably already know this, right? Then afterwards, there's the first part, then they used it in when the war broke out, they started using it in the war to increase yields and all that stuff. And then you got into Mr. Demings came about, and he started implementing the quality systems and all that stuff. And now, of course, we are using it more and more. And one of the reasons, by the way, one of the reasons why the COVID vaccine is getting delayed is not because they're not able to make it, but the testing is going to take a long time. And how do they test it? They go through a lot of DOEs. They have to go through a lot of factors, a lot of variation, underlying conditions and all that stuff, right? So DOEs have been used in several industry. Yeah. My favorite wine is the Meiomi Pinot Noir. Okay. So if anyone of all want to send me a gift, that's what you need to send me. So if you look at this, right, if you look at this wine in 2014 and 2018, I got this from the websites. You can see that they're all blended differently from different grapes, right? Why did it do that? In order to maintain the consistency of the taste. Okay. And once you have that consistency, once people start liking what it is, right, is that taste, they need to keep on maintaining it, right? And that's what gives them success, right? In fact, when I was doing this research, I found that the company has sold for just one brand of wine, right? Just this one was sold for $315 million. So that's a lot of money. But they use this in the wine industry, food industry, everywhere. Yeah. So why don't mold? So if it's so useful, why don't molders use it so often? Because of the misconceptions, right? Number one, they say it's too complicated. One needs to understand math and statistics, right? Then they say it takes a lot of time to perform these studies. There's a lot of waste of material and resources. It takes a lot of time to measure all the cavities, all the dimensions, or all the runs. Then I need to learn how to use a software, right? And interpret the results. Yeah, I mean, Minitab is a fantastic software, right? I mean, if you guys know how to use it, more power to you guys, right? But I always say for what we want to do, it's like taking an airplane to the grocery store, right? You want to go to the grocery store, you don't need to go by an airplane, right? It's just like that, right? So use something simple, right? So then the other thing they'll say, you know what? I don't need to do all this DOEs because I can come up with the same process by doing without a DOE, okay? Yeah, but you can come the same process, but there's a lot of other things that the benefits that you get, which I'll talk about here very soon, right? So for all these reasons, people don't do DOEs, right? So let's go into molding now, right? So effect of packing, if I want to study the effect of packing pressure, then if you see here, if I increase the packing pressure from 4,000 plastic PSI to 8,000 plastic PSI, then the dimension goes from 1.726 to 1.735. What does this mean? An increase or decrease in the packing pressure. Oops, that's not 400, it should be 4,000. An increase or decrease in the packing pressure by 4,000 psi increases or decreases length by 9,000 of an inch. Right? So what did we do here? We systematically went and performed two experiments, one at low pressure and one at high pressure, right? And looked at the dimensions and plotted the results, right? This is a dotted line that you see here because this relationship can be anyhow. Okay, there's always a curvature there. If I have the time, we can talk about it, especially in molding. We have to be very careful because always a physical limitation to the tool. You cannot keep on packing it and dimensions keep on, you cannot go on increasing, right? Because of that thing, right? So this relationship can be anything in there. And so what have we done? We have done two experiments, one low and one high. But now I say that, so this is the most basic DOE, right? Because you've systematically done these experiments. Then I say that I want to also now look at the effect of melt temperature on this, right? I did packing pressure first, so I did melt temperature second. So what do? I repeat the same high and low experiment at the high and low, the melt temperature. So I end up with 4 experiments. Then I say I want to add mold temperature. So now I add another 4 experiments because I'm going to repeat the same 4 at the high and low of the other one. So I end up with 8 experiments, right? If I add one more to it, it becomes 16 experiments, right? So as I keep on increasing the number of factors or processing parameters, the number of experiments keeps on becoming double because I'm studying low and high. They're called as levels. At 2 levels, they keep on becoming double, right? In fact, by the way, we have all those of you all who do scientific molding studies, all of you all have already done a DOE, right? Look at your gauge seal study. Part weight versus time. What have you changed? You have systematically changed the times and ended up with and collected the part weights. That's a DOE. Okay, so all these things are DOEs also, right? So changing the 11 plus 2 factors and coming up with the dimensions and finding the dimensions is basically what is called as a designed experiment, right? But here's the problem is that if I've got 1 factor and 2 levels, I end up with how many? 2 experiments, right? If I go to 2 factors, it becomes 4. Then that becomes 8, right? That becomes 16. If I now decide I want to do 3, low, medium, and high, I get 3 experiments. And then if I decide 2 factors, becomes 9 experiments, right? So as you start increasing this, you'll find out the number of experiments that you need to run is equal to number of levels raised to the number of factors. That's a formula. So now if you do that calculation, you will find that at 13 factors, at 2 levels, you end up with 8,192 experiments, and at 3 levels, you end up with almost 1.6 million experiments, which is impossible for you guys to do, right? So what do you do in this case? That is one reason I think a lot of people have not, one more reason I should say, that people have not done, they don't do DOEs in industry. Says, man, there's too many factors in injection molding. First thing, there are only 11 plus 2, by the way. Okay, I've heard numbers like when I start my class, people say, how many factors? I said 30 factors, 40 factors. No, it's just 11 plus 2 factors. Okay, so if you say there's too many factors, right, on this stuff, that's the first reason people don't do DOEs, or one of the reasons, like I said, they don't do DOEs, right? But that becomes an impossible job. So what do you do in that case? I'm not going to get into any of the details, but this is where our friends, the statisticians, they come into the picture, and people like Ravi who do data analytics, they come into the picture and say, okay, you know what? It's not that. There's something called as orthogonal arrays, and there's something called as interactions. What we do is that we take all these things and we do confounding in there. And then basically now, instead of running all those experiments, 8,000 experiments, you can run a few of those experiments, and those few are now going to predict what the quality of your part is, right? And so that is what statisticians do. And like I said, I'm not going to go into details of this because of the time limitation here. I do teach some of it in my class. And if you want something really detailed, of course, Ravi can come and teach that too for you guys also, right? So they do these things called as fraction factorial experiments, and there's several models out there for DOEs, right? There's Fisher methods, Taguchi methods, so on and so forth, right? And you can do all this analysis and then come up with what is the factors that are most important for you. Okay, like I said, Minitab is one software that you can use. Nautilus software, which I'm going to show you here, which I made very simple. I'm going to show you guys, right? But then how do you select the factors? And I'm sure you guys are interested in this, right? How do you select the factors, right? So I can't run these many experiments. So first thing is that you understand you have the molding side of it. Everything comes from the PVT diagram. Okay, you've got a pressure, volume, and temperature graph. Okay, that's what you do, right? In injection molding, what are you doing? You're taking plastic and melting it. So you're giving it temperature, you melt it, and then you pressurize it and inject it into the mold. And as it is being injected inside the mold, its part is cooling down. So the change in the volume, which is their shrinkage, right? So anything that is affecting the PVT is what is extremely important in your DOEs. Okay, now, so if you look at it, right, mainly it is the pressure, volume, temperature. So pressure and volume. Volume is related to the pressure also, as in, right? All these things are of course related to these things, right? So pressure, volume, and temperature are important, and therefore, basically, if you look at this, we do our scientific molding studies and we start looking at our 11 plus 2 factors. In this case, I have made only 11 factors to keep it simple, and I've put short side and transfer together, so you see them as 10 factors here. So if you look at this, right, how do you select a short side and transfer position? It's fixed at 95 to 98% fill. So do you use it for DOEs? No, you don't use it for DOEs because you want to keep that percentage fill the same. How do you find out injection speed? You did a viscosity curve and you select your injection speed. So do you want to go slower? No. You want to go faster? No, right? You have set your injection viscosity curves there, injection speeds there. Injection pressure on closed loop machines is fixed. The machine takes what it wants, right, from there. Okay, it takes what it wants from what's available to it. So if you change that up and down, it's not going to matter, right? I've called this the holding pressure, as this is actually pack and hold pressure. Yes, use this for DOEs, very important. Holding time is fixed for cold runner systems. For hot runner systems, you may have to use it. Cooling times, use it for DOEs, yes, because it's a cooling rate. Melt temperatures are yes for amorphous materials. Mold temperatures are yes for crystalline materials. Okay, and again, why is that? Cover that in the class. So we have set our screw rotation speed based on a melt temperature study, looking at the homogeneity, and we also set our back pressures based on a scientific back pressure study, right? So this is a based on data, we have set those numbers there, and therefore, if you look at it, you can basically, the factors that you want to study for use for DOEs is basically always your pack and hold pressures, always your cooling times, always your melt or mold temperature. If it's in olefins, you may have to use both. May, the word important is may. You may have to use both of them, and it may be a holding time, we would say, hot run system. And therefore, in most cases, if you're a cold runner mold, right, you can, 3 factors is more than sufficient in there, right? And therefore, like I said, you don't have to do all the 1.6 million or 8,000 experiments. You can get away with running 8 experiments, and that's going to give you all the low-hanging fruit that you need, right? Is injection speed important? In some cases, yes, right? It'll have to go on case basis, but in most cases, no. Okay, is back pressure important for doing DOEs? Absolutely not. Okay, why is that? Because the effect of back pressure, let's say on a scale of 1 to 10 is 2, whereas packing pressure is 8. Okay, so what do you go change? Packing pressure in that case, right? So having said that, I'm going to quickly go to my software. It's going to be very quick. There's a nice 23-minute video on my website. That's a short version. That's how powerful my software is. But I'm going to go to the software here and show this to you guys. And this is my software. There's a home screen. There's a database here, all 3 databases. On the project, you can see all these icons out here: melt preparation studies, 6-step study, the scientific molding studies, plastic process sheet, and so on and so forth, of which I'm going to go into the DOE. And I'm going to show you how easy the DOE portion I have designed this here is. You can see in the DOE, the first window is with a drop-down list. You select the factors: cooling time, melt temperature, holding pressure. Of course, you can type your own in here. But notice this: I only have 5 factors. You cannot add more than this. Is it easy for us to put, say, all the 11 factors here? Yeah, but we don't need it. I want to keep it simple for you guys. Okay. This is step number 1. Step number 2: put in your highs and lows numbers. What do you want to study? I want to study holding pressure from 800 psi to 1200 psi, because when I did my process window below 800, I got short charts. Above 1200, I got basically flash. So these are my physical limits in here, right? I'll tell you what this precision number here is soon. So this is 2. Number 3, put in all the dimensions that you want to check: your nominal values, your tolerances, sample sizes. This is not statistical analysis. Very important, very important. You just need to check 3 to 5 parts. That's it. You don't need to check 30 parts. Okay. If it's a family mold, select to which part this dimension belongs to, and you simply click on worksheet. That is it. That's how simple the software is, guys. Okay. It spits out these 8 experiments here. You can see there's 8 runs. We do full factorial experiments, 3 factors, 2 levels, so that becomes 8 experiments. You run one confirmation run, and these are basically the 8 experiments that you run here, plus 1, 9. Go to the molding machine, run your parts, collect all the data, put all the data here. In here, you can also collect an Excel sheet and dump it in here if you want. Actually preferable. And then, so experiment 1 through 8, sample 1, sample 2, sample 3 for all the dimensions that you see here. And then you simply come in here and click on analysis. That's it, right? Like I said, I've achieved my goal of making life simple for the molder. Okay, so What does it give you? I'll tell you the most important. There are several tabs here on the top. You can see it'll tell you the most important tabs. Tornado chart. What does it tell you? The most important factor for that dimension, that cavity. See, it says here C. Holding pressure is the most important one. Okay. So now if I tell you go change the dimension of the part, what are you going to change? You're going to go change holding pressure. Are you going to touch B, cooling time? No, because cooling time makes no difference on that part. So don't even touch the cooling time. So now see, you're making data-driven decisions on this, based on this. Okay, then you come to the process windows. Okay, because we know melt temperature and holding pressure, the two ones that are important, right? This is my cosmetic process window. That means inside this, I can make good parts. Below 800, I got short shots. Above 1200, I got bad parts, right? So now if I want to hit nominal on this dimension, this solid green line that you see, if I click on that, anywhere I click on that, it tells me at 530, 962 and 11.5 seconds, I will hit nominal on that dimension. This is your data, this is your machine, this is your measurement systems. The software is only analyzing it. Okay, how accurate is this? I will show that to you very soon here, right? So now that means what? I can come in and draw this window inside this, which is the dimensional process window, inside which you'll always mold parts that are to spec. So if I maintain my temperatures between 486 and 544 and 834 and 1060, I'll always make parts that are going to be to spec, and that becomes my dimensional process window. Okay, so you can do this. We can also simulate the process. So this is cavity 4, this is cavity 5, this is the length of the part, this is the lower spec limit, nominal and upper spec limit. At a setting of 5, 10, 11.5 and 1000 psi, the predicted dimension of cavity 4 is 15.0589, for cavity 5 is 15.0749. I can now come and change the process right here, right? If I change the process, what happens? You can see the X is going up, this will become red, out of spec. I can decrease my cooling time, I increase my melt temperature, right? I can do a complete simulation of the whole process right here for you, right? This is the length of the part, the diameter of the part, this is the other diameter of the part, the diameter 2, and you can see here very clearly that this blue column that represents the change you can make in the molding process, the dimensions basically, right? That is completely outside my spec limits. What does this tell you? That it's impossible for you to mold these parts to spec, because you're going to get flash or short shots. You can't go down, so you have to have a steel change in this case, right? Or look at this dimension. No matter what you do, it will never go to spec. So you can actually eliminate inspection from this one. Okay, so the software, you can come in and say, okay, tell me the best process. We can also optimize based on the dimensions and the cavities that you select. It tells me my most optimum process spec, and come to nominal here, right? It tells me basically that my most optimum process is 550, 15 and 10,000, 1025 psi here. Okay, so we also give the most optimum process, but okay, that's optimum process. What about these parts here? Okay, 550, 15 and 1025, we have something called as suggested dimension changes coming here. 550, right? 10 seconds. Oops, sorry, 10 seconds and 1025. See, now it tells me diameter 2 is 15.6 and 15.8, so about 16 thousandths away from nominal. If I go change the steel on that cavity by 16 thousandths, I will again hit nominal on that dimension. I know now the software also tell you how much steel you need to change. Okay, so the several things that you can do with the software. Basically, now it tells you what is your, for example, so what is it tells you your process windows. It can tell you, you can find out the most optimum process. It can simulate the process, and all this stuff software can tell you. Yeah, and then that's how you come up with the preferred process, right? And then you come up with the the process that you really need to run, and give dimensions and see what the windows are and all that sort of stuff in there, right? Once you have the molding process, you can record the molding process in the plastic process sheet, and under compatibility, the software will also now tell you, right? Selecting that thing here, when I do display compatibility, the software will also tell you which machine, other than the machine that you ran it in, which machine will it fit in as far as percentage short size goes and residence time goes and all that stuff. But that is one tab. The second tab is process machine compatibility. So machine 5 is where I came up with a good robust process based on scientific molding and DOEs. And now I can now predict, give you the process for every other machine in the database. What is red is not acceptable. What is green is acceptable. So now if I decide that I want to write in this H machine here, I come in here, select H, I click on go. The software will now come up with a process sheet for that machine where you have never run this before. All based on calculations, by the way, in this case, right? So this is a process sheet. How did you come up with this? You know that this process is robust because you have done the DOE on this, right? Most importantly, okay? So again, it takes me almost 1.5 hours to show you the software. There's a very quick 23-minute video. Please look at it on the software side of it. But I want to get back to my presentation here because I want to take some questions also. So a good example is this. There's a company that is always making bad parts and they always had issues, customer returns, right? So what did I do? So there's a part that had sync and the length was important. So we did this. First thing I did is a process window, sync and flash, and decreasing the pressure would bring the parts in spec, but then the chances would increase the chances of sync. Right? I'm sure you have seen this, right? So this is how the process window was. So how did I know? Only because I ran the DOE in this case, right? And so what do you do in this case? You simply come in here, center the process right in this, center the steel down here based on the DOE data again. And now first thing you choose a robust process with a nice wide window on both sides as just your steel. And now you're going to have a good robust process. In fact, in this case, there were 3 dimensions that the customer literally stopped measuring after this. And before that, they would always get rejects from their customers because of either sync or dimension or spec. Right? How good is my software? Here is from my seminar. One of my seminars, I get this every single time, but this is the one that I actually made the PowerPoint for. You can see here that the actual and the predicted. So we run this. This is run number 9, which is the confirmation run. If you look at the actual and the predicted, the difference is almost 1,000, actually less than 1,000. That's rounded up there, right? That's how good we are. Our software it predicts the dimensions out there for you all, right? Then the process transfer. How good is that, right? So if you look at it, we moved from a customer of mine moved from 50-ton to 100-ton machine. Using that printout that I showed you, they were able to get the dimensions 2 tenths of a thousandths and almost 1,000ths, 9 tenths of a thousandths, right? So again, excellent prediction is what we get through the software. Okay. Again, everything is data, guys, right? There's no going and let me change this, let me change that, right? And that's the biggest thing that is very important, right? Another customer, they save $100,000. It's right here, irrigation company. They save a lot of money on this. By doing, again, this is all based on doing DOEs. They found out that they could run the parts much better, have reduce inspection, all that stuff. Again, without doing a DOE, you would never know how fast you can run a mold. You would never know where the dimensions are and how soon the dimensions can go out of spec, right? The cost of software, by the way, is equal to the cost of 1 mold trial on about a 75-ton press. Okay, it's $2,000 a year. We constantly add stuff to it, and that's why it's a subscription-based model, just in case you guys are wondering why. There's lots of stuff that Ravi and myself are working on, very cool stuff that should be coming up here very soon also. Yeah, company in the UK, they ended up saving just on inspection, right? They saved almost 30,000 pounds. You can see this number in here. Okay, so I always do a 2-stage approach. Scientific molding is one part of it. And then basically I've got the second part, which is the design of experiment. So I highly suggest that you guys do these things. Again, these flowcharts are available at no cost and for free. So send me an email. I'll be more than happy to send you this information. Absolutely. In there, right? Again, one more thing I want to tell you, there's fantastic technologies out there. For example, there's pressure sensing technology. But again, if you don't have a good, robust process, those technologies will not be useful for you guys, right? So I think this is great stuff to maintain and to monitor your processes and look at the parts and so I think if you're going to be using this again, I think you guys should be using doing DOEs also, right? So it's very important to set alarm limits. How do you set alarm limits, right? This all should be based on data, right? Again, you may have the world's best machine out there. Okay, you might have very good machines. I know I've heard very good things about Sodick. Machines. I have a customer down in Texas that uses, I think they've got a lot of machines down there. They are mainly they mold for small parts, but I know that Sodick makes machines that are even larger ton machines, and I'm sure the technology transfers the same technology. So definitely, like I said, you may have the really good machines, but again, you need to also have good processes. So this is also very important, right? So why don't molders do DOE very often? Let's look at this, right? It's very complicated, is it? It's not, right? It's very simple. I showed you, like 4 clicks and you have got analysis. Do I need to understand math? You don't need to understand math. Does it take a lot of time to perform? Not really. 9 runs or 5 shots. Usually in 2 hours, you should be finishing the runs. Okay, do the calculations, guys. Okay, within 2 hours, you should be running all the DOE parts. Okay, waste of material and resources. Yeah, it is that amount you use. If you don't do DOEs now, you're going to be wasting all that material in production, because you're constantly running to the presses and having bad parts in there, right? It takes a lot of time to measure all the cavities. That is absolutely true, but there's a way that I can tell you how to reduce measurement. We can let's talk about that offline, but there are ways. Yes, measurement is the one that takes the most time, but again, the small dimensions and all that stuff, I've got a way that you can get around, and I'll talk about that, right? I need to learn how to use software. Is that true? No, just look at my software. It's like 4 clicks. Yeah. I can come up with the same process without going through the DOE. Yes, but how robust is that process, right? What do you know? How do you know what you need to change in there, right? Is the process efficient? All that stuff, right? You will not find out until you do DOEs, right? One main important thing that I've seen, very important, is that you have to have management support. Your management has to understand that DOE is a valuable tool. If the management does not agree with that, then it's going to be a challenge for you to implement that in your company. Okay, so that's it. I think I made time. Yeah, so that is the thing. So now, having said all this stuff, right, I just hope that you guys agree that DOEs are not complicated. Yeah, so I think I'll stop here, and I think I'll take some questions. I believe there are some questions here, and then I know, let's see here. Weston, you want to unmute yourself and see?
Yeah, Suhas, I have a few questions that we have had come in, and I think I'll just read them down and let you answer each one if that works.
Okay. And just to let you guys know, I'm going to do my best to answer all the questions. If it's going to take a longer time, I want to get to everybody's questions, and also feel free to email me, and we can talk about it also at the same time. Yeah, Weston, go ahead.
Sure. The first one came in, will the slides be available after the presentation?
Yeah, so some of the slides will be available to you guys after the presentation. I'm also planning to put this video on my website, so you guys can probably, or somewhere that you guys can view the presentation. But yes, absolutely, I'll give you some information about the slides. Yes.
Next one, is ANOVA used in Nautilus?
It is. We had hit that thing only because, like I said, I wanted to keep it easy. But come September 1st, we will be giving that we'll be reactivating that tab. Answer is yes.
And following up on that, how this approach can be transferred to FDA requirements for process validation?
Yeah. So the software is validated, and I will give you. I will send whoever asks the questions. Please send me an email, and I'll send you the document and the validation document. Right. We have this software is used across all industries, and it's not specifically a medical software, but a lot of my software customers are medical people.
Very good. Next question, Suhas, can the software be used for only molding or other processes as well? Like reactive extrusion or foam extrusion parameters?
Yeah, it's only used for injection molding, and that too, it's not used for silicones yet. My expertise has been thermoplastic injection molding. That's very important, by the way. I've been doing DOEs for in injection molding for now since 1996, but I don't have the domain expertise, and therefore my software is not ready for silicone molding or any other industry out there. Okay. And
Would
so
that include thermoset materials to us?
exactly, it's not for thermosets either, because I don't know how what the mechanics and what the physics and the whole thermoset industry, how it works. I mean, I have an idea, of course, but I have not worked on it, right? So I worked on the floor for 14 years, hands-on. I still do that, by the way, and I understand that, but I don't understand thermosets, and so please don't use the software for silicones and or for thermosets at this point.
Very good. Next question that came in, what percentage of variation allowed in multi-cavity hot runner mold?
That's a very, so I actually wrote an article on that, and it all would depend upon the tolerances you're looking for. Okay. Why don't I do this? Why don't I, that's a very long discussion. Okay, when you're doing that. So for example, if I'm molding forks and spoons, is completely different from if I'm molding a very tight tolerance part, right? And so let me get through the other questions here, and if I have the time, I'll come back to that. But Weston, you can send me these questions by email, right? All these questions.
Yeah.
Okay. All right.
Yeah.
So I'll remember to answer this question, and then we can send it out. Again, the person who asked that question, please again get back to me if I've not answered the question. I'll answer that.
Okay. How do you conduct the screw recovery and back pressure studies?
Yeah. So it's a simple study. Again, I have a procedure that I can send you guys out. No problem. So basically, think of it as you increase the screw rotation speeds, your melt temperature goes up. So you do a simple study of melt temperature versus screw rotation speeds and find out what's the right one. Back pressure, what's back pressure doing? Back pressure is compacting a melt to the same, you want it to compact the melt to the same amount of melt density. So what we do is that we run 10 short shots and find out what the variation is at different back pressures. And then select the back pressure. And what I'm also finding now is that once you do it, say 5-6 times for a certain material, then you know what is for the material. You really don't have to do it for every single mold. Again, please, that person send me an email. I'll send you the procedure.
Excellent. Next question to us: flow rate and temperature of cooling medium are actually factors of a DOE. Isn't mold temperature a response actually?
Well, if you have a thermocouple in a mold, you can look at the temperature and see what you need to achieve that temperature. So an input, yes, you're right. The input would be what is coming from your thermolator or your mold temperature control unit. But once you know what that is, let's say that you're getting a 2 GPM is at 80 degrees Fahrenheit is giving you a mold temperature when you're running the parts at 90 degrees. Then I think maintaining that is important. But yes, it is always an input.
Very good. You mentioned that variation might be due to part design, dimension of part, and every part is unique in its own. How can software decide process setting without having initial data to drive?
I don't think so. I follow that question very well. But the software, everything you're doing in the software is all data that you have generated from your inspection, right? So you have taken the parts and you have measured the parts and you have put it in there, right? So what I mean by that is that how does part design affect your dimensions? Can affect your dimensions or your, let's say CPK. I'll give you a good example is that there was a part that was I hope you guys can see my webcam. Is my webcam on?
Yeah.
Yeah. So there was a part that was, say, this long, and there was a very thin section in this area, and there was a dimension that they had to measure out here. Okay, but the gate was here. So it was such a long flow length that by the time the plastic came here, it always froze up, and they had a lot of difficulty filling that section, and they wanted good process capability in that section, right? So we measured it after doing DOEs, right? And we found that there's nothing really affecting this, that you could not do anything with the process to affect that CPK. So what had to be done? You have to move the gate to a certain location so that you can basically fill that section. So it was a tooling problem, and it was a part design problem, because now they could not do that because they did not, that surface was basically a cosmetic surface, right? So it was more of a, that is how, what I'm saying is that part design, that's what it affects your molding process, right? Again, I hope that's how, I hope I answered it correctly, but I'll be more than happy to, you guys can give me a call and we can talk about that also.
Very good. Next one that has come in is, are there any locks or controls in place that will prevent people from updating the machine information once it is entered?
Yes, in the software we have got user access levels, so you can have different levels in the software. Yes.
Excellent. Can you provide some insights into the different molding requirements between molding color chips and mechanical testing specimens, including tensile bars?
Read that question again, please.
Sure. Can you please provide some insights into the different molding requirements between molding color chips and mechanical testing specimens, including tensile bars?
So I've not done any of that stuff, but I'm just assuming that with color chips, you need good mixing. When it comes to processing of the tensile bars, you basically need to have, you know, a good molding process and consistent molding process. I would still advise you guys to go through not necessarily DOE, but at least the scientific molding side of stuff, because the dimension in a dimension of the test specimen is not going to be important to you.
What will the preferred shot size be?
It should always be based on the material. It should be at least 20%. If you want good robust process, at least 20% to 75%, sometimes 80%, right? Exceptions to the rules. Well, if you've got a very heat stable material, you can go less than 20%, maybe, and fast cycles, you can go a little less than 20%. I have a company that molds parts successfully at 8%, an acetal part, but runs very fast. But in most cases, 20 to 80 is a good rule, or 20 to 70 is a good rule.
Excellent. And there's a question here from India. Is the software available in India?
Yes. Software is available, yeah, all throughout, anywhere. Yeah, it's a download, so you guys can download and basically use it. And again, we give a 30-day trial, and if you guys want some help in the DOA analysis, I'd be more than happy to do that even during the trial time at no cost. So that I don't want to sell the software if it's not going to be useful to you guys. And we want to be very clear about that. Okay, I'm not a guy who's just going to sell it because I want the money part of it. I want it to be useful to you guys, because if somebody buys the software, doesn't use it, they're going to say the software is useless, which is not true. So please, if you want to try it out, get me involved. I'll help you and walk you through that, and I'll help you with the, what do you call it, with the analysis also.
Excellent. Could we use the software before mold manufacture for DOEs of the molding process?
No. So this is, you can't do that. This is, so there are simulation DOEs is completely different from actual DOE. For example, Moldflow does a simulation DOE, right? But that's before the mold is built. But this is not before the mold is built, because you don't know what the size of the mold is, the size of the parts are. The answer is no. I have some questions here. I think you may be having the same one. Go ahead.
Okay, there's a few more here that have come in over message as well. You were going to talk about the precision column in your software.
So remember, I showed you how I was changing the temperature and the pressures in steps. That's what the precision is. Okay. By the way, everywhere in the software, you guys are still seeing my screen. Everywhere in the software, we have got a question mark here, which basically shows you a visual help button. Okay, and that will also tell you what each of those things are in there. But I was simulating that software. I was simulating the process up and down, and that's what is the precision number.
In the machine tab, would you recommend we add each machine a separate entry if we have multiple screw sizes?
Yes. Because yes, especially if you want to generate a process sheet for that machine, because the process will change because the intensification ratio changes. And this is an electric machine.
Okay. How can we handle or remove hesitation at the time of filling due to filling micro parts due to curvy or sharp edges in design?
So that actually would so that actually would so I think I've for some reason I've got that question here, Weston. It says
Okay.
due to hesitation, more pressure required to fill the temperature. First thing, is there a facility in the software that handles that hesitation? No, this is not. The software is strictly a DOE software, and we can't use that as a. If they can study that, we could probably use it as an input. But I would suggest that this is not the software for solving that problem of yours. What you need in your case is to have a good machine that is not going to have that hesitation. There's two hesitations, by the way. This is hesitation of the screw, so you're going in different phases. That's one thing. But there's also hesitation of the melt, which is extremely difficult to control because plastic melt is compressible. Yeah, that is very difficult to control. So if you have a good machine, at least you're halfway there. Okay, and definitely you're saying micro parts. I think Sodick machines are very well known for micro parts.
Looks like a last one here, Sue asked before there's a second Q&A section I think you're seeing.
Okay.
There's a question here. Is there an option to purchase this as a standalone rather than a subscription-based software?
Well, we don't have that. There's a lot. The issue with that is that number one is Microsoft, on which our platform is based, the software is based on. They keep changing a lot of things, and the software will stop working after, let's say, 5-6 years, and we can't support it, even less than that, right? That's one thing. Second thing is that you will miss out on all the updates. If there's any updates, you will not get the updates, and that's the reason. And believe me, right, is that if you can reduce one more change in your shop, that's going to pay for your software. So it's not, that's the reason we suggest. And that's the reason we used to be that way. We went to the subscription model only because there's a lot of updates we're giving, and the one that is coming out in September is we got some more really cool features in there.
Excellent. Looks like there may be 10 to 15 more questions. Are you seeing all those, Suhas? I can let you.
I'm not, but I think,
okay.
I don't know if you're are people still online?
Yeah.
Okay.
Yeah, we still have a number of them here.
Okay, let's keep going. I mean, let's keep
okay.
going. I can answer them.
Excellent. First one was about LSR materials, which you spoke of. Next one, how would these approaches be done using overmolding?
Very good question. Actually, this is very good. I think so with the overmolding, you have to basically your first shot is now going to be actually a factor for your second shot. Okay, and therefore you have to first come up with a good robust process for your first shot. And once you know that you have a good robust process and hit the dimensions, right, and make sure that you can mold good parts on there, now you first fix the first shot and then you start the DOE on the second shots.
Great. Are there any variations or variants to the software, or is this just a one purchase required? Which I think you've covered.
It's on my website. There's the software versions and stuff. There's on my website. If you guys go to the software section, you'll see that.
Excellent. Do we get CPK values?
There's a quality section that we can give you, but there's a different section. It does not come in the DOE side of it. But yes. And at the same time, Ravi's expertise. Ravi has got his expertise is all quality systems, and so there's a number of things that he can also provide, and that's what I was telling you about the updates, right? And what we are going to do is actually we're going to have a full quality system into our software too very soon, and that would be actually included in the price if you go to a subscription model. Right? It's going to be a very complete detailed software, including SPC and all that sort of stuff. It's not in the September one, but it will be coming up very soon.
Very good. Question here on injection speed. Why is injection speed not used as a factor in the DOE? They say they have found that they're able to increase the window by using minimum and maximum injection velocities from the viscosity study.
Yes. So it's not that it's not used for, it's not one of the low-hanging fruits for certain type of parts. I believe I mentioned that, right? On certain long parts, you might see that the viscosity injection speed is an important factor, right? So you can use that for injection for that. But once you typically with the viscosity curve, once it's selected and say, this is my injection speed, then you typically don't want to change it, but you can absolutely use that. The only thing you have to be very careful there is there's something called as interactions that comes into picture with when you look at injection speeds and melt temperatures, because the temperature changing as you inject slower and slower. So interactions become a little bit more prominent in those cases. But you can use it, yes.
Excellent. Can you use the software if they use recycled resin in the process?
So if you've got consistent recycled material, see, that's the reason I'm smiling is because you cannot have consistent recycled material, right? It's always changing, and so it's difficult. Yeah. So if you're using a lot of recycled material, I think what you should do is if you've got a good incoming section, then I think you need to have your spec set as low and high, and then do the DOE at low and high, and then you can basically use that for process windows and DOEs, right? But recycled material is always a headache. I'm going blank right now, but that the word where you've got two opposites in the same word, I'm missing that. That's what that is. Good quality recycled material that doesn't exist. I mean, it's not consistent. Sorry.
Oh, okay. What parameter can be considered to correct or minimize warpage?
Warpage is always a resultant of uneven cooling. Okay, so really until you do so from it starts with part design. You can't have thick and thin sections. That's one thing. Your mold design has to be good. So you got even cooling on both sides. So it's all big. Those are the first things, right? And then when it's come to warpage, unless you do a DOE with cooling times, maybe injection speed in this case, and then with pack and hold pressures, right? Sorry, not pack and hold pressures, more with the melt temperature, mold temperature. Until you do a DOE, you will not know what the answer is. But it could be any one of those things. Like I said, it's all dimensions. I'm not saying only warpage. All dimensions are part dependent, machine dependent. It is also orientation dependent and material dependent. All these things.
Excellent. Can the VP switchover be a variable for DOE?
It can be. It can be a switch. So when you do a VP switchover, what happens is your percentage fill changes. It can be, but it's not recommended, right? What are you trying to achieve? So basically, if you change your VP switchover, it's almost the same as changing your pack and hold pressures. So I think you should try both and see. Right, but we typically don't. We want to use 95 to 98% fill and injection. And therefore we don't use that. I don't use that.
Excellent. There's a question looking for if you can provide a QC module details.
Please send me an email.
Okay.
We have not finalized everything completely yet, and Ravi is online, and I'm sure he's there. But we will. Please send me an email, and then we will that person, and then we will talk about that. Yeah, there's a lot of stuff that's coming in the software. Let you know. We're also working, yeah, automotive and things like that. So we've got a lot of requests, and we will do that.
Excellent. Does your software help develop regression techniques used to measure less details for the parts to determine overall dimensions?
Not at this point. I mean, we have got things we can do, but we have not. We don't want to make it too complicated. But and we don't. That's the thing. That there's a lot of IP in that we don't. We have, but we've not exposed it.
Excellent. Looks like we're down to the final couple questions here, Suhas.
Okay.
For every combination of injection pressure and filling time, there's a volumetric shrinkage.
Just a second. Just repeat that.
Sure. For every combination of injection pressure and filling time, there's volumetric shrinkage. Okay. How can we control that volumetric shrinkage?
So volumetric shrinkage, I mean, that is going to show up in dimensions. Look at that, it's going to show up in a dimension. So as long as you're going to be, as long as you know what the dimensions are, I think as your process changes up and down, right, you can look at the dimensions, and that is what is going to giving you the changes will going to reflect the volumetric shrinkage. But again, please, that person, please email me. I'm not understanding, not want to know why you would want volumetric shrinkage rather than actual dimensions of the part. So I'll be more than happy to discuss with you guys. Right. So as I change my process and do DOEs, I find out what the dimensions of the parts are, which is actually in between what's happening is a volumetric shrinkage that's going on.
On one subscription to us, how many people can use that?
You can buy multiple seats. It's just like you've got SolidWorks and all the stuff. You can buy X number of seats, and X number of people will get access to that. So there's a network version, which is $2,600. $2,000 is a standalone version. Network version, one seat is $2,600. And then every additional seat, whether it's standalone and or the network version, is additional $1,000. So for $3,600, you'll get 2 seats. For $4,600, you'll get 3 seats.
Very good. You recommend to optimize the back pressure, screw RPM, and suck back by performing the optimization study prior to running DOE.
Yes. You have to prepare your melt first. And once you have a good melt, because then you should start the rest. In fact, you should do that before you start scientific molding study those.
Okay, next one here. For direct valve gates, can hot runner tip temperatures be used as a DOE factor?
Yes, answer is of course yes. But if you have a large part, then I'll tell you this, you're not going to see a huge difference other than cosmetics. You won't see dimensional difference. If it's a small part, then it will make a difference. But the answer is yes.
Okay. In your presentation, you'd mentioned 95 to 98% filling before switchover. They want to know, is that volume or mass?
Great question. It's always a question that's asked, is it volume or mass? And the answer is extremely simple. If you look at the formula for weight is equal to volume multiplied by density. And since density stays the same, if you get 95% volume, it's also 95% weight. Right? It's the same, actually it's the same thing. Okay. Now, looks can be deceiving. So if you've got a thick part, you might fill the whole skin because of fountain flow. But it really doesn't matter. But again, I said, don't get stuck on the 95 to 98% numbers as such, right? As long as you're slightly short, you're good. But make sure that you're always hitting that same 95% part every single time. Okay, that means if I am doing my validation and doing process development, I got 5.125 is my injection only short weight. The next time you run that mold, make sure you got 5.125. Is it 95 or 98? Don't get too hung up on that number.
Very good. That looks to end the questions that I have over here, Suhas.
Yeah, Ravi just texted me that the term I was looking for is oxymoron. So, saying that you've got consistent regrind material is an oxymoron, or not regrind, sorry. Consistent recycled material is an oxymoron, not regrind. Regrind can be very consistent, by the way. Okay. Again, those of you who want that I want to discuss that, I'll be more happy to discuss that, right? But you're getting recycled material, that means you're getting from somebody else, right? Consistent recycle, unfortunately, is an oxymoron.
Very good. Very good. Well, I guess that's a great way to leave it, huh? And I want to say thanks for everybody that stuck around for the Q&A. Thanks to everybody that joined us today and actually stuck through the technical difficulties early. I think once we got that ironed out, it went really well.
Yeah. And
thank you, Suhas Kulkarni. Thanks, Ravi. I want to thank Bennett Howard and Len Hampton for starting us off there this afternoon. A lot of great info on it. We will be hosting upcoming webinars as well. There's Leonine Technologies with Raul coming up on July 8th on his multivariate shrinkage sensor technology. Coming up on July 15th is going to be Conair. And we have Sam Rajovic doing that one for us on their TrueFeed Micro feeder system. So following those later down the line, we'll have New Tech Automation, as well as our long-term partner here, Beaumont Technologies. So keep an eye out on your emails. There'll be more invites coming, and really appreciate everybody sitting through it with us here today. Have a great afternoon.
Yeah, thank you, everybody. Thank you very much.
Thank you for having us over.
Yeah, thank you. Bye.
All right, thanks, guys. Everybody take care.